This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today's paper tackles a critical challenge in predictive maintenance, developing machine learning models robust enough to diagnose faults in rotating machinery despite significant environmental and operational variations. The authors propose a continual learning approach. What are the key limitations of traditional machine learning approaches in this context?
Traditional methods often fail because they're trained on static datasets, assuming all possible fault types are present during training. Real-world scenarios are far more dynamic. Variable loads, temperatures, speeds, and even the emergence of entirely new fault types render these models ineffective. Retraining the entire model each time is costly and time-consuming. Training only on new data leads to catastrophic forgetting. The model forgets previously learned faults.
So catastrophic forgetting is a major hurdle. How does this continual learning approach address this, and what other second-order challenges does it consider?
The approach addresses catastrophic forgetting, lack of plasticity, inability to adapt quickly to new data, and the need for both forward transfer, using past knowledge to improve future learning, and backward transfer, refining past knowledge with new insights. It uses a modular architecture, a shared feature generator, and domain-specific classifiers. This allows the model to grow as new domains, different operational conditions, emerge without overriding previous knowledge.
The modularity is interesting. Can you elaborate on how the feature generator and domain-specific classifiers interact?
The feature generator extracts common features from the input data, vibration, or acoustic signals. Each domain-specific classifier then builds upon these features to specialize in a particular domain. This shared feature extraction is efficient and prevents interference between the classifiers.
And how does the experience replay mechanism work to mitigate forgetting?
The system stores a small subset of data from previous domains. Crucially, it doesn't just replay randomly. It prioritizes replaying data from domains that showed the highest error rates in the previous training episode. This focuses learning on the most informative past experiences.
This boosting-inspired replay strategy is key. How does it facilitate both forward and backward transfer?
By prioritizing domains with high errors, the model refines its understanding of those challenging areas. This benefits both future learning, forward transfer, as the model learns to generalize better, and past learning, backward transfer, as the model improves its accuracy on previously seen but difficult domains.
The paper mentions experiments with different domain ordering strategies. What were the key findings?
3 strategies were tested: lowest accuracy first, highest accuracy first, and alternating. Starting with the highest performing domains yielded the highest overall accuracy, but also the most forgetting. The alternating strategy provided a good balance, minimizing forgetting while maintaining high accuracy.
And what about the impact of replay buffer size?
Larger buffers, more past data, led to higher overall accuracy, but slightly increased forgetting. A balanced selection strategy, half from high error, half from low error domains, minimized forgetting, though at a slight cost to overall accuracy.
Finally, how robust is the model to noise and data corruption?
The model showed good robustness to mild and moderate noise levels. Performance degraded under high levels of corruption, but still remained competitive. This suggests the method is reasonably resilient to real-world imperfections.
The paper highlights 2 consistently challenging domains, 7 and 11. What might account for this persistent difficulty?
The paper suggests inherent difficulties within those domains, possibly due to unique data characteristics or noise levels. Further investigation is needed to pinpoint the exact causes.
What are the key limitations of the study, and what avenues for future research do the authors suggest?
The main limitation is the reliance on simulated data. Real-world data is essential for thorough validation. Future work should focus on real-world datasets and explore the influence of various operational and environmental factors on the model's performance.
The authors also mentioned exploring different architectural choices. Why is this important?
Architectural choices such as network depth, width, and the use of specific layers, e.g., normalization, skip connections, can significantly impact the model's ability to balance stability and plasticity in continual learning. This is an area ripe for further investigation.
The choice between regularization and replay-based methods also warrants further study. Can you elaborate on this?
Regularization methods aim to find shared representations across domains, while replay-based methods, like the one presented here, focus on selectively revisiting past data. The optimal approach likely depends on the specific characteristics of the data and the nature of the continual learning problem. More research is needed to understand these trade-offs.
This has been a very cycled discussion. Thank you for explaining the intricacies of this continual learning approach for rotating machinery fault diagnosis. The modular architecture and boosting-inspired replay strategy seem particularly promising for addressing the challenges of real-world applications. Thank you.